Hello everyone, welcome to my channel Learn Physics with MPZ. I am Dr. Mrityunjay Prasad Ghosh, currently working as an assistant professor at SR University, Warangal, Telangana, India. So today we are going to discuss an important topic, that is Kirchhoff laws. So we will discuss the basic concepts of Kirchhoff laws. So there are two Kirchhoff laws, one Kirchhoff voltage law and another Kirchhoff current law. Both laws are based on conservation of energy and conservation of charge. So let's start the discussion. So in our previous class, we have discussed about several circuit elements like voltage source, current source and resistor. We have also discussed Ohm's law and its application. So we have gone through the principle and statement of Ohm's law and its application, right? We have also solved several numerical problems based on Ohm's law. So in this lecture, we will discuss about the Kirchhoff voltage law and Kirchhoff current law. So let's move to the next slide. So now we will discuss about the Kirchhoff laws. So there are two laws as we have discussed. One is Kirchhoff voltage law and another is Kirchhoff current law, right? So these two laws are given by Gustav Robert Kirchhoff. So he was a German physicist, right? So as we have discussed, Kirchhoff laws are the fundamental principle which are based on the conservation of energy and conservation of charge, right? And these laws are used in analysis several circuits. So Kirchhoff voltage law is based on the principle of conservation of energy or the law of conservation of energy, right? Whereas the Kirchhoff current law is based on the law of conservation of charge or the principle of conservation of charge, right? Did you get it? Moving to the next slide. So now, what is the statement of Kirchhoff voltage law? So the algebraic sum of voltage around a closed loop at any instant is equal to 0. So the algebraic sum of voltages around a closed loop at any instant is 0, right? So what is a loop? So a loop is a path that terminates at the same node where it started from. So a loop is a path where this path ends at the starting point, or the path must have same ending or starting point, right? So this is called a closed loop. So the algebraic sum of all voltages around a closed loop at any instant is 0, right? So algebraic sum of all voltage around a closed loop at any instant is equal to 0. So this is the statement of Kirchhoff voltage law, right? So if you want to express the Kirchhoff voltage law in terms of mathematical form, then it looks like summation Vn, where n equal to 1 to and any number n. So small n equal to 1 to and any number n, Vn equal to 0. So sum of all voltages across or around a closed loop at any instant is equal to 0. So this is the mathematical form of Kirchhoff voltage law, right? So Vn represents the nth element voltage in the loop, where n is the number of elements in the loop, right? So this is the mathematical form of Kirchhoff voltage law, right? So Kirchhoff voltage law can be expressed in another form or another statement, right? So which is the algebraic sum of voltage sources is equal to the algebraic sum of voltage drop that are present in a loop, right? So the Kirchhoff voltage law can also be expressed as The algebraic sum of all voltage source present in a closed loop is equal to the algebraic sum of voltage drop across different circuit element, right? So these two voltages must be equal that are present in a loop, right? So what do you mean by algebraic sum? So algebraic sum of voltages means the magnitude and direction of the voltage, right? So algebraic sum of voltages means the direction and the magnitude of the voltages. So you have to consider magnitude as well as the direction of the voltage while taking the algebraic sum of voltages, right? So while taking the algebraic sum of voltages in Kirchhoff voltage law, you must need to consider the magnitude as well as the direction of the voltages, right? So what is the statement? That is the algebraic sum of voltage source present in a closed loop is must be or must equal to the algebraic sum of voltage drop across different circuit elements present in a closed loop, right? So this is the statement of Kirchhoff voltage law, and this is the mathematical form of Kirchhoff voltage law, right? So here, if this is a circuit element, right? So if the potential is dropping or the if there is a drop in potentials, so if you move from this direction to this direction, from positive to negative direction, this is a circuit element. So there is a drop in potential, right? So you need to consider negative voltage. So if there is a circuit element in a closed loop circuit, and if you take this direction, right, and there is a drop in potential, if you take the direction from my left side to right side or the positive to negative, then there is a drop in potential. So you need to take negative voltage. Whereas if you take this direction, this is a circuit element from negative to positive, so there is a rise in potential. So you need to take positive voltage. So while considering KVL in a closed loop, if there are several circuit elements and if the drop in potential is found in a certain direction, then you need to take the negative voltage. And if the potential in a certain direction or the considered direction is raised, then you need to take positive voltage, right? So if there is a circuit element, right, resistor, right, and this is a closed loop, so you draw a closed loop first. So there is a source, battery source. So consider this is a closed loop. So current is flowing this direction I, right? This is the positive pole of the battery and this is the negative pole of the battery, right? So in this direction there is a drop in potential. So you need to take the negative voltage, right? This resistance is considered is a R, then V minus, we need to take the negative, so V minus IR equal to 0, right? So this is the statement of Kirchhoff voltage law. So V minus IR equal to 0, or you can say V equal to IR, right? Because the algebraic sum of all voltages present in a closed loop must be equal to the voltage drop of the circuit element that are present in a loop, right? So it is clear now. So now moving to the next slide. So what is the application of Kirchhoff voltage law? So the Kirchhoff voltage law or KVL is used to find out the unknown voltage and current in a electrical circuit. So if there is a closed circuit, then you need to calculate the unknown voltage and current that are flowing in the circuit or in the closed loop. So you need to find out the unknown voltage and current by using the Kirchhoff voltage law or KVL, right? So it helps to form the mesh equation or the loop equation for a circuit analysis. So if you want to do circuit analysis of a particular circuit, then to form the mesh equation or the loop equations, the KVL is useful, right? It is applied to designing and testing electrical circuits, right? So KVL is used to design and examine electrical circuits, right? It is useful in detecting faults and troubleshooting circuits, right? So sometimes if there is a fault in a circuit elements or in a circuit, so you can easily detect the fault in the particular circuit by using the Kirchhoff voltage law or KVL, right? It helps in analyzing the voltage drop across different components in the circuit. So if there are different circuit elements in a closed loop or in a electrical circuit, so by applying KVL, you can easily calculate the voltage drop across the circuit element and the current through the circuit elements, right? You can easily calculate by using Kirchhoff voltage law or KVL. So now let's take an example, right? So this is a closed loop or closed circuit, right? So this is the voltage source. So there are three resistance. Let's take as a resistance, that is Z1, Z2 or Z3 or R1, R2 and R3, and the voltage drop across R1 or Z1 is V1, V2 and V3, right? Across Z1, Z2, Z3, take this as a resistance, right? So the voltage drop across each resistance, that is Z1, Z2, Z3 or R1, R2, R3 is V1, V2 and V3, right? So let's take, this is the direction of current. I current is flowing through the circuit. This is the direction of the current. The direction of the current is clockwise, right? So according to the Kirchhoff voltage law or KVL, the algebraic sum of all these voltages is zero, right? So the algebraic sum of all voltages at any instant in a closed loop is zero. So here voltage is Vs, then the direction is from positive to negative, so there is a drop in potential, so you need to take negative voltage. So we have discussed, if there is a drop in potential, then you need to take negative voltage, right? So here current is flowing from this direction, so here there is a drop in potential from positive to negative, right? So you need to take negative voltage, so minus V1. Similarly here minus V2, and similarly for the this resistor minus V3, right? So Vs plus minus V1 plus minus V2 plus minus V3 equal to 0. The algebraic sum of all these voltages is 0, right? So you can easily get Vs equal to V1 plus V2 plus V3, right? So basically it's a statement of conservation of energy, right? So KVL, so you can see here the sum of all voltage drop is equal to the source voltage, right? So there, this is a basically the conservation of energy, right? So by using KVL, you can easily analyze this circuit, and you can also find out that the KVL is the law of conservation of energy, right? So moving to the next slide. So now we will solve a numerical problem. So we will find out the current I through this closed loop and the voltage drop across the 15 ohm resistor, right? So we will calculate the voltage drop across this 15 ohm resistor and the current flowing through this circuit by using KVL or Kirchhoff voltage law, right? So here we have applied some sign, right? This is plus to minus, this is plus to minus. The voltage drop across 5 ohm resistance is V1, across 10 ohm resistance is V2, and across 15 ohm resistance is V3, right? And the direction of the current I is clockwise. Did you get it? So that is 5. Here there is a potential drop or drop in potential, so the voltage must be negative. So 5 volt minus V1, here also the potential drop is negative, right? So there is a drop in potential, then the voltage is negative. So 5 minus V1 minus V2, here from positive to negative, right? So there is a drop in potential, so it should be the negative. So minus 2, here positive to negative, so there is a drop in potential, so the voltage must be negative. So 5 minus V1, that is drop in potential. So V1 is the voltage drop across 5 ohm resistance, right? V2 is the voltage drop across 10 ohm resistance. So there is a drop in potential, so the voltage must be negative. So minus V2, then positive to negative here, because the direction of the current we have considered in clockwise. So minus 2, and similarly for V3, which is a voltage drop across 15 ohm resistor, and there is a drop in potential in this direction, right? So the voltage must be negative. So 5 minus V1 minus V2 minus 2 minus V3 equal to 0. So algebraic sum of all voltages in a closed loop at an instant is 0. This is the statement of KVL, right? So we can easily get by simplifying this equation, V1 plus V2 plus V3 equal to 3, right? And as per the Ohm's law, what is V1? V1, if I is current flowing through the 5 ohm resistor, then V1 equal to I R1. Similarly, V2 equal to I R2, or V3 equal to I R3. R1 equal to 5 ohm, R2 equal to 10 ohm, R3 equal to 15 ohm, right? So here 3 equal to V equal to I R1, R1 equal to 5 ohm. So 5I plus V2 equal to I R2. I and R2 is 10 ohm. So 10I plus R3 is 15 ohm. So V3 equal to I R3. R3 is 15 ohm. Then 15I1. 15I, right? I is current flowing through the circuit, which is flowing through the clockwise. So you can easily simplify. So 3 equal to 5I1 plus 10, 5I plus 10I plus 15I, right? So this is 30, I equal to 3. So I equal to 3 by 30. So I equal to I, that is the current flowing through the closed loop, is 3 divided by 30. So I, we will get I equal to, or it is 1 by 10, or I equal to 0.1 ampere. So current flowing through this circuit is 0.1 ampere. So now you can easily calculate the voltage drop across 15 ohm resistor. So by applying Ohm's law, across the 15 ohm, the voltage drop V equal to IR, where I equal to 0.1 ampere and R equal to 15 ohm. So 0.1 into 15, that is 1.5 volt. So by applying KVL, we can easily calculate the voltage drop across each element in a circuit and the current flowing through the circuit. So in this circuit, the current is 0.1 ampere and the voltage drop across 15 ohm resistance is 1.5 volt, right? So we have calculated the voltage drop across 15 ohm resistor and the current through the circuit by using KVL or Kirchhoff voltage law. Hope it is clear now. So moving to the next slide. So now we are trying to solve this problem. So we need to find out the voltage difference between the C and E point in the circuit. So in this circuit, we need to find out the voltage drop between C and E point, right? So there are two parts. This is one part and this is one part. So let's flip the circuit or redraw the circuit. So A, B, C, D. This portion, let's flip it, right? So if you flip it or redraw the circuit, so if you flip this circuit, right? Let's try to flip this part A, B, C, D. Let's try to flip it. So you will get here A, B, C, D, and here the same thing, that is H, G, F, E, or E, F, H, G, right? So you need to calculate the voltage drop across these 2 points. Then that C and E point, right? So we will calculate the voltage drop across these 2 points, or the voltage difference across these 2 points C and E, by using the KVL or Kirchhoff voltage law, right? So here we consider two current I1 and I2. This is loop 1 and this is loop 2, right? This is loop 1 and this is loop 2, right? So I1 current is flowing through the loop 1, which is counterclockwise, and I2 current is flowing through the loop 2, which is also counterclockwise, right, or anti-clockwise. So I1, I2 is the current which are flowing through loop 1 and loop 2, and the directions are counterclockwise or anti-clockwise, right? So here, so this is positive, this is negative. So if you flip it, so this 20 volt changes polarity, right? This is 20 volt, right? 20 volt battery changes polarity if you flip it, right? So here let's apply Kirchhoff voltage law in this loop, that is loop 1. So 20 minus 6I1 minus 5I1 minus 9I1, right, equal to 0. So starting from there, like this counterclockwise. So 20 minus, this is loop 1 and this is loop 2, right? So as applying KVL, that is 20 minus 6I1 minus 5I1 minus 9I1 equal to 0. So you will get easily I1, right? So 20 minus 20 minus 6I1 minus 5I1 minus 9I1. So 6 plus 9 equal to 15 plus 5 equal to 20. So 20 minus 20I1 equal to 0, or I1 equal to 1 ampere. So the current that is flowing through the loop 1, that is I1, is equal to 1 ampere. So now take the loop 2, that is EFGH loop, right, where the current flowing through the circuit or the closed loop is I2, which is a counterclockwise directional current, right? So here this is positive, this is negative. So 40 minus 8I2 minus 5I2 equal to 0, right? So algebraic sum of all voltages in a closed loop at an instant is 0, right? So 40 minus 8I2 minus 5I2 equal to 0, right? So 8 plus 5 equal to 13. So 40 minus 13I2 equal to 0, or I2 equal to 40 by 13, that is 3.01 ampere. So we have calculated the current through the loop 1 and loop 2, that is I1 equal to 1 ampere and I2 equal to 3.07 ampere by using KVL or the Kirchhoff voltage law. So now we need to calculate the voltage difference or the voltage drop across C and E point, right? So by considering the voltage difference between the point C and point E, that is VCE, let's consider this voltage VCE, right? VC is the voltage difference in between C and E point, right? So now consider that So VCE we need to calculate out, right? We need to find out VCE. So VCE, right? So these, to find out VCE, this current I1 is upward direction, I2 is downward direction, right? So minus 5I1, this voltage VCE plus VCE minus, so this is the whole current is moving in clockwise direction here, right? I1 and I2, the both current are clockwise direction, right? So 5I1, this is a 5 ohm resistance. So 5I1 minus 5I1 plus VCE minus 5I2, here in this direction the drop in potential increase, right, from negative to positive, so plus 10, right? So minus 5I1 plus VCE minus 5I2 plus 10 equal to 0, right? You know I1 and I2. I1 is 1 ampere and I2 is 3.07 ampere. So put the value of I1 and I2 in this equation. So you can easily calculate VCE. VCE is equal to 10.35 volt, right? So by applying KVL or Kirchhoff voltage law, we have calculated the voltage difference in between 2 points C and E, and the voltage drop is VCE equal to 10.35 volt, right? Hope it is clear now. So moving to the next slide. So now we will discuss the Kirchhoff current law, right? So we have already said that these two laws, that is the Kirchhoff voltage law or Kirchhoff current laws, are given by Gustav Robert Kirchhoff. He was a German physicist, right? So the Kirchhoff voltage law is based on the law of conservation of energy, and the Kirchhoff current law or KCL, which is based on the conservation of charge. So what is Kirchhoff current law? So this is basically the principle which is based on the principle of the conservation of charge, right? Here charge is conserved for Kirchhoff current law, and for the Kirchhoff voltage law, it is based on the conservation of energy. So the energy is conserved, right? So moving to the next slide. So what is the statement of Kirchhoff current law? So the algebraic sum of branch current at a node at any instant of time is equal to 0, right? So the algebraic sum of all current or all branch current at a node point, right? So node is a point where two or more circuit elements are connected, right? This is called the node. You know that. So the algebraic sum of all current or all branch current at a node at any instant of time is equal to 0. Or you can say that the incoming current at a node and the outgoing current at a node, so they must be equal. So incoming current must be equal to the outgoing current at a node, right? So what is node? So node is a point where two or more circuit elements are connected, right? So node is a point or junction in a circuit where two or more circuit elements are connected. So this is node. And what is Kirchhoff current law? So the algebraic sum of all branch current at a node at any instant is equal to 0. Or you can say that the incoming current must be equal to the outgoing current at a node point, right? So what is the mathematical form? So mathematically it can be expressed as summation in equal to 0, or n runs n equal to 1 to n, right? Capital N, where in is the nth current at a node and n is the number of branches connected to node, right? So we know that node is a point where two or more circuit element or branches are connected, right? So in is the nth current at a node and n is the number of branches connected to a node, right? So the KCL or the Kirchhoff current law can also be expressed as the algebraic sum of current flowing towards a junction is equal to the algebraic sum of current flowing away from the junction. So that is basically the incoming current must be equal to the outgoing current at a junction or at a node point, right? So the algebraic sum of currents means, so what do you mean by algebraic sum of current? So while you are taking the algebraic sum of currents at a node point or at a junction, then you need to take both the magnitude as well as direction of the voltages, right? Right. This is must be the current, right? You need to take the magnitude and the direction of the currents, right? Did you understand? So while taking the sum of all currents meeting at a junction point or at a node point, so you need to take the magnitude as well as the direction of the current. So in a simple word, the incoming current must be equal to the outgoing current, or the algebraic sum of all current meeting at a junction point or at a node point at any instant of time must be equal to 0. This is the statement of Kirchhoff current law, right? So current entering the node must be positive current, or the current leaving the node must be negative current. So the incoming current at a node must be positive, or outgoing current or the leaving current at a node must be negative. So you need to remember these two facts, right? Incoming current at a node point or at a junction must be positive, or the outgoing current or leaving current at a junction or node must be negative, right? So moving to the next slide. So now we will try to solve this problem. This is basically an example, right? So there is a node point n which is denoted as n, and there are several current I1, I2 and I3. So I1 and I2 and I1, I2 and I3, these three currents are incoming currents which are entering the node, and the I4 and I5 are the outgoing current which are leaving the node, right? So according to the Kirchhoff law, the algebraic sum of all this current is zero, must be zero, or you can say that the incoming current must be equal to the outgoing current at the node, right? So what are the incoming current? That is I1, I2 and I3 are the incoming current, and what are the outgoing current? That is I4 and I5 are the outgoing current. So incoming current must be equal to the outgoing current, or you can say that the incoming current you need to take positive current, and for the outgoing current you need to take negative current. So I1, I2 and I3 are the incoming current, so this should be the positive current, so I1 plus I2 plus I3, and the I4 and I5 are leaving, or the outgoing current, so the sign must be negative, so minus I4 or minus I5, or you can say the algebraic sum of all current meeting at a junction point at any instant must be 0, or incoming current must be equal to the outgoing current at any instant in a node or junction point, right? So incoming currents are I1, I2 and I3, which must be equal to the outgoing current, which are I4 and I5. So I1 plus I2 plus I3, that are the incoming current, must be equal to the outgoing current, that is I4 and I5 are the outgoing current. So I1 plus I2 plus I3 equal to I4 plus I5. So basically we know that what is current? Current I equal to Q by T, that is charge by time, right? Charge by time, Q by T. So it's basically a law of conservation of charge, right? So KCL is basically a law of conservation of charge, or it is based on the principle of conservation of charge, because I equal to Q by T, the current equal to charge by time, right? So incoming current must be equal to the outgoing current, so you need to understand, or you need to remember this at any junction point, right? So incoming current must be equal to the outgoing current. The incoming current I1, I2, I3 are the incoming current, which must be equal to the outgoing current, that is I4 and I5. So I1, I2 plus I3 equal to I4 plus I5. And KCL is basically a statement, or is based on the principle of conservation of charge, right? Did you understand? So now moving to the next slide. So now we are trying to solve this problem, and we need to find out the current I6, right? So there are three nodes A, B, and C, where in node 1 or node A, I1 current and I4 current are entering the node and I2 current is leaving the node, right? Similarly for B, the I3 and I6 current are entering and I1 current is leaving the node, right? Similarly for the node C, the I2 and I5 currents are entering the node and I3 current is leaving the node, right? The value of I1, I4 and I5 are given. You need to find out the value of I6, right? So we will apply KCL, that is incoming current must be equal to the outgoing current at a node point or at a junction. So we will apply this principle, or we will apply KCL to find out the current I6, right? The value of I1, I4 and I5 are given. We need to calculate I6, right? So first take node A. So at node A, I1 and I4 current are incoming and I2 current is outgoing, right? So incoming current must be equal to outgoing current. So I1 plus I4 equal to I2, right? The value of I1 is 2 and I4 is minus 1 ampere. I1 is 2 ampere and I4 is minus 1 ampere. Here I1 plus I4 equal to 2. So what is I2? I2 is 2 minus 1 equal to I2. So I2 is 1 ampere, right? So you have calculated I2. This I2 is 1 ampere, right? Similarly for node C, I2 current and I5 current are incoming current, whereas I3 current is outgoing current, right? So I2 plus I5 equal to I3, right? You know I2 is 1 ampere. We have calculated. What is I5? I5 is given, that is minus 4 ampere, right? So 2, we need to calculate I3, right? So I2 plus I5 equal to I3. What is I2? That is 1 ampere. I5 is minus 4 ampere. So 1 minus 4 equal to I3. So I3 is minus 3 ampere, right? So now we consider node B, right? This is the node B. Yeah, at node B, the I3 and I6 current are incoming and I1 current is outgoing, right? So incoming current must be equal to the outgoing current. So I3 plus I6 equal to I1, right? We have calculated I3. I3 is minus 3 ampere, right? What is I3? I3 is minus 3 ampere. We need to calculate I6. So I6 equal to I1 minus I3. I1 is given here. I1 is 2 ampere and we have calculated I3 is minus 3 ampere, right? So I1 is 2 ampere and I3 is minus 3. So minus plus minus plus 3, right? So 2 plus 3. So I6 is 5 ampere, right? So we have calculated I6, which is equal to 5 ampere. So by applying KVL, oh sorry, by applying KCL, the Kirchhoff current law, in this circuit, we have easily calculated the I6 current, right? Hope it is clear now. So moving to the next slide. So in this lecture, we have gone through the Kirchhoff voltage law, Kirchhoff current law, and their statements, right? We have discussed the application of KCL and KVL, which is used to find out unknown voltage, unknown voltage and currents in a circuit. Sometimes you can calculate the resistance, unknown resistance, by using KVL and KCL, right? So basically it is used to calculate voltage and current in a loop or in a circuits, right? In a circuits or in electrical circuits, there are several loops. So you can easily calculate the current and voltage inside the loop, or you can find out the voltage drop across a particular circuit element, or if or if you can use these laws to find out unknown resistance also, right, if the other parameters are given. So in this lecture we have also solved some numerical problems based on KCL and KVL, Kirchhoff voltage law and Kirchhoff current law. Hope this session is useful to you, right? So you have understood all the basics principles and the basic concept of KCL and KVL, Kirchhoff voltage law and Kirchhoff current law. Thank you. Thank you for your patience.